Class. Today I am going to explain the photoelectric effect. So first I give you a very brief introduction. Consider a metallic surface, and if you shine a light or electromagnetic wave, the electron on the surface of this metallic kick out of the metals, and we call them photoelectrons. This effect is called the photoelectric effect. So scientists knew about it many years ago. When they tried to explain it in terms of the classical electromagnetic, they didn't, so they got stuck. So Einstein published a paper in 1905 and explained this effect by using the quantum mechanics. It was the first time that Einstein used the concept of the discrete energy to explain something, and he got the Nobel Prize for explaining this effect. So he told us that instead of considering this one as a continuum energy, let's consider that this light is made of a bunch of particles that we call them photons, and the energy of this light is equal to n. N is the number of photons, can be millions. X is a constant, we call it Planck constant, and F is a frequency. And H, we know that is a 6.626 times 10 negative 34 joules per second. So you see that this term is very different from the classical one. The classical one, let me write it for you. You have seen in the general physics. In classical, we have this energy. Let me write it. Energy or intensity is proportional to the electric field, or something like this. You have seen this one before. So you see that they are very, very different. So again, this is the first phenomenon that can be explained in terms of the quantum mechanics. Okay, before I go ahead, let me make something clear. There is a difference between photoelectric and fermionic effect. This one, electrons are kicked out by light. This one, electrons are kicked out by heat. So don't mix up them together. So how could we run this experiment? Here you see a very schematic setup. We have a chamber, glass chamber. It should be vacuum. Why? Because when electrons are kicked out, they hit the air molecule, so they're gone. So it is why that we make it vacuum. And here is a metal surface. It can be any metal like potassium and nickel or anything. It's connected to a battery, and the ammeter is here. This one connected to the negative, this one is connected to the positive, this one is a detector or a type of collector, or we call it cathode anode. So if we illuminate this plate with the light or monochromatic light, what happens? Again, because of the photoelectric effect, electrons jump out of this surface and they move. Some of them can reach here, and then we can here see the current that flows through the circuit. Very simple experiment. I will show you the experimental setup. So for this case, you have to carry out 3 different experiments. First, you keep the frequency constant. I told you monochromatic, and you change the intensity. You increase the intensity. Okay. Then, on the other hand, you keep the intensity constant and change the frequency. And finally, based on the graph that I am going to explain soon, you can measure the Planck constant. Remember, we know that what is the Planck constant, but we want to measure it and see that how could we measure it by this way and how is accurate. So we have 2 graphs here. If you, for example, if you keep the frequency constant, you see that below a frequency that we call it the threshold frequency, nothing happens. For example, if it is a potassium, if you illuminate with the red light, nothing happens. It doesn't matter what is the intensity. And again, it is in the contrast to the classical physics. But if you increase the frequency to almost blue, you see that there are some electrons that jump out of this metal. So there is a threshold frequency. For any matter, this one is different. So after that, if you increase the intensity here, you see that there is a straight line. So remember, Again, this one should be at least threshold frequency. And after that, if you increase the intensity, the amount of light, of course, you have a straight line. And of course, your data should be some dots here. Finally, you will have a line like this. Here, again, this equation you can find in literature. The kinetic energy of these electrons is equal to E, charge of electron, V is the voltage of this battery. Let me write it here. So this is V, voltage of the battery. And HF, frequency, here you should subtract from W. W is the work function. It's the amount of energy that they need so that they can separate from these metals. Again, this one depends on the metal. It's different from sodium, it's different from potassium. So, if you divide everything by E, you have something like this, and it is the equation that we have here. You see that? So, the slope of this line is the H over E. H over E. Okay. So, if I change the intensity, I have something like this. Now, if I keep the frequency constant, of course not below the threshold. Below the threshold, nothing happens. So we are not interested at all. Above the threshold, if again I keep the intensity constant and change the frequency, go to higher frequency, what happens? I have a graph like this. So for high frequency, we have more intensity. For lower frequency, we have the lower intensity. And it is interesting that you can graph some of them, and all of them converge here in the potential. We call it a stopping potential, that we call it V0. It means that I make it negative with respect to this, so it doesn't allow the electron to hit it. And this one just depends on the type of metal here. Yeah, it is interesting. We call it a stopping potential. So graph number 1, graph number 2. And it is for experiment 1, you should have a graph like this. And for experiment 2, you have to have a graph like this. How could you measure or calculate the Planck constant? If you have this graph, it's easy. You find the best slope. It's easy to find it. And the slope is OH over E. We know that what is E? E is the 1.62 times 10 negative 9. And you can find H from here very easy. Also, I can add something here. I can add measuring H and work function. Why not? So you can also measure the work function from here. If you continue this line, the y-intercept is a negative work function divided by, again, I know that what is E, I can find the work function. So I can find the work function by any method that is here. This is all about today's experiment. In the next video, I'm going to explain the experimental setup. We use a type of mercury light as a source, and use a different filter so that we have the monochromatic effect.